Our second talk is by Mohammad Mirzadeh from Mechanical Engineering, Direct Numerical Simulation of Supercapacitors Charging Dynamics.
Thank you. So my name is Mohammad Mirzadeh, and I'm fifth-year graduate student at Department of Mechanical Engineering. And today I'm going to talk about supercapacitors. And so supercapacitors are energy storage devices, pretty much like batteries, with two major differences. One, they can charge really fast, usually under 100 seconds. Two, they can be charged and discharged many, many cycles, on the order of hundreds of thousands. And so there are many different applications for these devices nowadays. One of them, for example, here, this is a crane. And people have figured out that if they combine supercapacitors with usual diesel engines, they can save up to about 40% in the fuel consumption. This is another application. These are purely electric buses in China, and they run completely on supercapacitors. And because supercapacitors can charge so fast, whenever they stop at the stations and the people are getting in or getting out, they can connect it to power lines and they can recharge the bus. You can use supercapacitors to do water filtration and water desalination. So if you have salty water and you flow it through a supercapacitor, you can filter all the salt and all the ions, and you get fresh water that you can drink. Or you could do the reverse process. You could combine fresh water with salty water, and using a supercapacitor, you could extract the net energy. Now, what I'm interested in is to do computer simulations to study these devices. And particularly, I'm interested in knowing what is the effect of the geometry, what is the effect of the port geometry on how fast these things can charge, how much charging can store. And here what I'm showing you is one particular curve which shows the percentage of the supercapacitor that is charged as a function of time. And the dots, the black dots that you see here, they are direct computer simulations. And they're compared to two existing models that people have been using them for the past 50 years or so. And what I'm showing is that both are wrong. And using our computer simulations, we were able to actually derive a new model that can do a very, very good job of prediction. And so we think that now we understand these devices very well. And so the next obvious step is trying to optimize these devices for better performance, for faster charging, and for more storage charge. And so the basic idea is that we can get a sample from our colleagues who do experiments and create a computer model of that sample, and then run our computer simulations to figure out how much charge that can be stored in these devices, how fast they can charge. And then if we're not happy with the results, we can run other computer algorithms to optimize these devices for an optimal performance. And then we can give it back to our colleagues so that they can build it and test it and see how well it does. And then we can repeat this cycle many, many times. And so hopefully at the end of the day, we get something that is fast and can store a lot of energy. And hopefully we can somehow solve the energy crisis. Thank you.